Okay, let us quickly go through what we were doing in the last class. We started this business of something called the self-adjoint operator. And what we said was that this guy is 1 for whom it's a linear operator. So we'll call it L. So L operating on some function f, the inner product of that with G, if that inner product is going to be equal to the inner product of L operating on G and F, you call it a self-adjoint operator. Okay? And of course, the boundary conditions have to be given to you because you are performing some kind of an integration. So before we went ahead, we said that there is a small word of caution that even though a particular operator can be self-adjoint, it can also be not self-adjoint because it all depends on what the conditions are that are going to be over the domain that you are talking about. So, but we said that the self-adjoint operator is a linear operator that comes about in the so-called Sturm-Liouville system. And the Sturm-Liouville system is something that is useful to us when we are looking at separation of variables towards solution of the partial differential equations. And so this is d dx of px y prime plus qx y equal to lambda w, which is a weight function, and the variable is y. Now there are certain conditions on p's and q's and w's. This is a regular Sturm-Liouville problem. We're going to see the periodic Sturm-Liouville problem later today. But these are the only 2 classes that we are going to be seeing. Other classes of the Sturm-Liouville problem, we are not going to be so much interested in this particular class. And the conditions are alpha 1 ya plus alpha 2 y prime a equal to 0. And once again, notice that the conditions are homogeneous. Okay, so that's important. Alpha 1 plus square plus alpha 2 square greater than equal to 0 only ensures that both your alphas are not equal to 0. That's about all that it is going to ensure. So then we did a decent amount of algebra. We wrote this fellow down and then we went ahead and, so the reason why we are interested in this is because if you've got a self-adjoint operator, and that equation is going to be ending up with an infinitely many real distinct eigenvalues. Okay? And the eigenfunctions of corresponding to these eigenvalues form an orthogonal set of basis functions. Okay? So just to jog your memory a little bit, the orthogonality of the basis functions was important. And that was kind of the basis for the Fourier series that we had talked about. But here there is a small problem. The orthogonality is with respect to that weight function w. The weight function can be equal to unity, which it is when we talk about sines and cosines. But later today we are going to look at an example where the weight function is not 0. And you need to be careful when you are talking about the orthogonality. And the inner product, therefore, is going to be defined as fx gx wx dx. The w in the past, when we were using the Fourier series, was equal to 1. Now that guy raises its head, and you have the inner product as fx gx wx dx. And of course, the demonstration is a little bit algebra intense, not that bad. We did this last time. And what we said was that when you open up these brackets and do a decent amount of algebra, you're going to get certain terms that are going to cancel off, certain terms that are going to be remaining, and once the algebra was done, we said that if you are going to want the self-adjoint nature to be verified, then only that term had to be equal to each other. Okay? And now you need the boundary conditions, because you are going to have evaluation of that function at the ends, which is A and B. And there is another little bunch of algebra that needs to be done, and we did part of it. We didn't do the whole thing. We just said that, okay, it is straightforward brute force algebra, so you go ahead and do it. And what you found is that the so-called self-adjoint nature of the Sturm-Liouville problem was verified. And this is once again the regular Sturm-Liouville system. So the regular Sturm-Liouville system is that, and the most powerful part of this is that you have these eigenfunctions which are going to be orthogonal to each other, and if they are orthogonal to each other, then in principle you can represent any function which is within that function space in terms of these eigenfunctions. So that's very powerful. And so what we also said was that, okay, so this is the periodic Sturm-Liouville system that we are going to be seeing today. If the PA is equal to PB, remember we have d dx of Px y, and this we said when you have the y prime on it. So this is that Px that we are talking about. Okay. So if this Px or Pa is equal to Pb, Ya, which is the function at the two limits, so this was A, this was B, Ya is equal to Yb and Y prime A equal to Y prime B, that forms a periodic Sturm-Liouville problem. We'll see that in just a little while. We also said that all second order linear ODEs of the form y double prime plus pxy prime plus qxy equal to 0 can be written as Sturm-Liouville equations, and this is the self-adjoint form of the equation, and this is why we are interested in this whole business here, because when we are talking about the partial differential equations that we will be looking at, we do end up with second order linear ODEs, and all of these guys can be written in the Sturm-Liouville form. We'll look at one example later today. And this is something that I just flashed up there. I'm not going to do that because once again it's just brute force algebra, and you just go ahead and start with that equation, but the final result is important. And the equation that we had, we are going to be able to represent it in the Sturm-Liouville form, and again later today we are going to see what is the use of representing it in this particular form. Okay. So this is where we were. Okay, then we started looking at an example, and this was an example that had already shown up when we were looking at the heat equation that we had. And if we compare it with the Sturm-Liouville system, this is easily comparable, straightforward. The lambdas, once again, you have to be careful with what are the values for these lambdas. So for one last time we did lambda equal to 0. We showed that the result is a trivial solution. Remember the previous time when we worked this out, we said that we looked at e to the minus of lambda square t as the vehicle to understand lambda equal to 0 comes up with a trivial solution. Now we have used the other equation, which is the x direction. That's why we did this algebra. So we showed that this guy is going to end up in a trivial solution. Similarly, lambda equal to minus k square, the function is going to end up with exponentials. Those also are going to be telling us that the lambda equal to minus k square ends up in a trivial solution. The only option therefore remaining was lambda equal to plus k square, and when you go ahead and look at this, you get your eigenfunctions as y equal to sine n pi x by L. This was the same thing that we had in the past. Okay. So nothing new except that we are now saying that whatever we have done in the past is falling in this bracket of the Sturm-Liouville system. All right. Now, the reason why we started all this business of the Sturm-Liouville system was this question here, where we said that we had a situation where we had a gradient boundary condition on one side, and we did all this algebra a couple of classes ago. And when we came up with the solution, what we found was that the eigenfunctions still were sine of kx, but this k guy was not a constant. Okay, so if k is not going to be a constant, then you really have no business to say from trigonometry that sine kx is going to be orthogonal with any other sine kx. But nevertheless, we just went ahead brute force and said that even though they are not orthogonal, I'm going to go ahead and find out what the coefficients are, because I have no other option. Okay. So you assumed that they are orthogonal, and then the rest of the methodology was standard. The px, therefore, we could say was equal to the summation of those integrals, and we said that sine kmx and sine knx are orthogonal to each other. That's why that's put up in red there. We did not look at the Sturm-Liouville system at that time, so that was put up in red. And we found out the coefficients, and once again in red I am saying that this works only if or because the eigenfunctions are orthogonal, since the differential equation, which was the one, the ODE, was in the Sturm-Liouville form. Okay. So the Sturm-Liouville form, the reason for getting there was this particular situation, and the other situations are some things that we will be looking at. Okay, so this is why we started this whole business of the Sturm-Liouville equation. Okay, so you started this business, and now you find that those sine km's and kn's are indeed orthogonal functions. Okay, because the equation and whatever the associated conditions were amenable to the Sturm-Liouville system. So we'll look at one more example today, and then we are going to wind the whole business up. Okay. So this is where we were when we quit last time, and before we start this business, now we will go ahead. So whatever we have done was a regular Sturm-Liouville system, and now we are going to be looking at the periodic Sturm-Liouville system. And before I go ahead and do that, let me just quickly discuss your mid-sem paper, and the marks have been uploaded. So if you just put your attendance, it's much easier for me to distribute your answer books. So the performance was, I should say, very good. The maximum marks were 50, and the high in class was full 50, and the low in class was 20, and the average was about 32. Okay, so it's a very healthy average, I should say. Okay. Um, uh, there are certain comments I would make at the end, but as of now, let us just go ahead and look at the questions that were asked and the solutions associated with those questions. So the first question was phi of t plus integral of this. This is straightforward in the sense that the integral itself is the definition of the convolution integral, and you were supposed to go ahead and solve this by using the Laplace transform method. And I should say that most of you did not have any trouble at all with this question, and the solution has been uploaded, and I don't think there was any trouble at all which anybody faced except for a couple of students, and those students should be a little bit careful in future. All that you had to do was to take the Laplace transform on both sides and realize that Laplace transform of this convolution is the product of the Laplace transforms. That's all that needed to be realized. And you take Laplace transform on both sides and you get this, and use any of the online tools to go ahead and invert it, and you have the solution. Okay, so very straightforward. And the second part was to go ahead and get the derivative of this function. And again, even this question was fairly straightforward, and it was nice to see. I don't think there was anybody in class who did not use the Leibniz rule. I think there was just one or two people. So everybody is on very, very strong footing here. You had to use the Leibniz rule, go ahead and integrate this guy, and once again it's just a matter of brute force algebra, and you would get to the solution. And I think 90% of the class had no issues with this. Okay, so everybody had even the final answer correct, okay, which is surprising, but that's fine. Okay, the next question was slightly more involved. And you were supposed to use this transformation u equal to f times y and convert the differential equation into that. Again, part A was just brute force, just putting in the numbers, and most of you had no trouble with that. Okay, you just had to put in the numbers and go ahead and do the algebra, and there was no trouble at all. And you could get the algebra and you could get what those 1, 2, 3 are. Okay. Subsequently, in the next part of the question was where some of you, I'm not saying most of you, some of you don't even read the question properly. For some strange reason, you just don't want to read it, and you just go ahead and say that, okay, I know something about this solution, and I just say that u is equal to some kind of f of this and g of that, and then you just f of x has been given to be equal to x. You just substitute it and get the answer. Okay. Now, that was not what was being expected from you. You were expected to do a little more as part B. Of course, I'm not overly harsh if you have done that, but definitely a penalty was put for that. Think about a procedure to directly obtain the solution of the original non-homogeneous differential equation, and I think half the class did not even bother to say anything about that. Okay, so that's where some penalty was imposed. The other thing was to go ahead and then those of you who have actually read part of the question, and it says that you are going to say that the homogeneous part is going to be satisfied by a particular function. That you do, but then you don't read the rest of the question. Okay. So these are the common mistakes that were there, for which some penalty has been put, and the solution once again was not difficult. Some people did have trouble with algebra, I must admit, but otherwise there was not much. The other thing that needed to be worried about was when you were given the other equation, which was in a form which was not exactly in the original form. The original form was this guy here, right, u double prime plus something. The given form was x square times u double prime. So you had to convert it to the original form before you could just go ahead and use the final expressions that you had obtained, and that is where some of you made errors. But otherwise, by and large, I think 75% of the class had no trouble with that either. Okay, now this was the question where many people had trouble, and this is where I was harsh in correction also, for the simple reason that this was done in class in some sense. Okay, so a equation was given, and you were told to get the solution about the x equal to 0 point. And I must admit, most of you did realize that it was a singular point, and then you went ahead and used the Frobenius method. The Frobenius method was all fine, but and then you did the algebra, and finally, when you go ahead and come to the last stage, right, you get this the recurrence relation is obtained, and you get two recurrence relationships because you had two roots. And this was exactly the same example that was worked out in class, where I said that the two roots may or may not give you proper solutions. And one after the other, after the other, after the other is just simply saying r equal to 0 is that, r equal to nu is that, and I'm going to just say that the solution y1 is equal to cx to the n plus r equal to 0, cx plus. Remember that at that time in class also, I forget what the exact example was, we said that one of the solutions blows up, and this was exactly that case. Okay, when your m, which is the parameter, becomes equal to nu, it blows up. And many of you conveniently say am is equal to am plus 1 into 0, so it is a converging series. Okay, you are going the other way around. Okay, so you are getting a series that is blowing up, which means that one of the solutions, that's what Frobenius method had told you. The larger of the roots is going to give you the solution. The smaller of the roots you better be careful with. You may or may not. In the happy situation, you would get a root, but it may or may not end up in a solution. And just blindly saying that the other root is a1 ln is also not something that is acceptable to me. Okay. Unless, because the caveat there was a can be equal to 0. You have to tell me whether a is 0 or not. I'm not looking for what that a is. But you have to tell me what that a is, whether it is 0 or not. If it is 0, then something happens. If it is not 0, something else happens. Okay? And that's one of the reasons why we had said we had used the so-called Abel's theorem, which you can go ahead and use to get the second solution. Okay? So this was one question where many of you just simply did not take it to completion in a proper fashion. Okay, question number 4. It was framed to be a decently nice question, but it turned out to be a trivial question. Okay, so x, y, z were given, and we said you find out what is x prime and in terms of x, and When it was framed, of course, we thought that you would have to look at or you realized that the eigenvectors were there, but um, not all of you, but many of you just differentiated it, and then you just did brute force algebra to get the solution, which is fine, nothing wrong with that. But what was expected was to go ahead and, I am not harsh on anybody who did that. I've given full marks to most of the class. What you were expected to figure out was that solution looks like a solution where the eigenvectors are distinct and the eigenvalues are given up there, and therefore the matrix is a diagonalizable matrix. Okay. So once you have realized that, you just had to go ahead and take the inverse and obtain the solution. Many of you have done that. Many of you have gone through pages of algebra and obtained it. Many of you have used online resources to invert that matrix. All that is fine. Nothing wrong with that. And because this was algebra intense, if you did not get the final answer but everything was correct, I've not been harsh. I've given you most of the marks. The last question again was one where people have lost marks. Again, largely because you don't want to really go ahead and understand what's going on. Okay. This was something which is a nonlinear system, and I'm asking you to draw a phase portrait. 80% of you don't even want to draw a phase portrait. You just want to go online, see something, somebody is saying something, just copy that something down and say, hey, you figure out what the phase portrait is. I'm not going to do that. Okay. So I'm not saying everybody has done it, neither am I saying those who are here have done it, but many have done it. You were supposed to use the linearized form. Everything was there in the class slides. All that you had to do was to get the Jacobian and then go ahead and find the lambdas. And once you know what these eigenvalues are, you are very clearly seeing that it's a saddle point. And the worrisome part is that many of you claim that it's a saddle point, but you can't draw that portrait properly. Okay. The other part where lots of you have made errors is that you are clearly saying that the equilibrium point is not 0, 0. Okay. I must admit that in class everything we did was for 0, 0 as the equilibrium point, but we did clearly say that x prime equal to 0 and y prime equal to 0, that's where the equilibrium point is. And in this case, the equilibrium point was not 0, 0, but it was at 0 minus 2, as you can see. So that's where the plot is. Many of you are just going online and seeing all kinds of plots and plotting everything and expecting me to figure out what's there or what is not there. I'm not going to do that. Okay. So the linearization was important. That's why we had said that you draw those two lines along which it is going to be straight. The path is straight. That should tell you that I'm looking for the linear plot. I'm looking for the linearized equations. Okay. All right, the part B. This was something again straight out of the class notes, except once again, x prime and y prime were not equal to 0. Many of you want to make it 0 and plot it. I have not been overly harsh on that either, but you were expected to find out the eigenvalues and then the path lines. Okay. Remember that we are saying that these are the lambdas, lambda equal to 3, lambda equal to a smaller number, which is point something, and all of these paths, wherever they start, okay, so both of these are going to be such that the solution is going to blow up. So the solution is going to blow up in both of these situations. So wherever you are, initially probably it may want to go and then it's going to do that. It may even do this, but initially it would do that. Many of you are just simply drawing straight lines, which again is not what we are looking for. But many of you are performing the algebra all right, but then you are not going to or able to convert it from the algebra into the plot. Okay, so that was the exam. The final comment I would like to make here is that many of you are using online resources, which is fine. ChatGPT, DeepSeek, etc. people have used, and that's where I think some problem also lies, because neither of these two were able to give the phase plot correctly, nor were they able to give you that that Abel solution properly. Okay, so the others, the online resources were able to give properly. That does not mean I'm going to stop your use of that. You are welcome to use it. The idea of all of this is for you to understand what's going on and then be able to decipher whether the guy is doing things okay or not okay. Okay. ChatGPT was giving that even that series solution incorrectly. DeepSeek was doing it correctly. Okay. So these are problems which you need to, I don't use them very often, so I probably may not be using it correctly also, but all that I'm trying to say is that use your online resources properly, and pre-midsem everything was great. I mean, the online resources would work excellent. Post-midsem they are going to give you trouble. Okay, so be aware of this fact that post-midsem we are also going to ask you some concept questions, which these guys give you some answers. Just parroting whatever they are giving is not necessarily going to be okay. I'm not saying there's anything wrong with them. They're extremely good. All these online resources are extremely good, but just use caution when you are using the online resources. Okay. All right. With that, anybody have any major questions on the midsem that went by? No. Okay. How many of you thought that it was very easy? How many thought it was difficult? Oh, good. So if you don't raise your hand, then I can make whatever my opinion is. Okay, fine. But the very fact that the average is 30 out of 50 does show that many of you did very well on it. Okay, so if you have not done well, then it is cause for concern. And if you have done very well, you can pat yourself on your back, but beware that still another 50% of your grade is still up for grabs. Okay. Our next exam has already been announced to be in the first week of April, and the final date also is, I think, announced, but the room, etc., is not there. Okay. So if there are no questions on the midsem that went by, let's go ahead and continue with this business of the periodic term. I'll stop 5 minutes earlier today so that I can distribute your answer books and you can go to your next class on time. All right. So the periodic Sturm-Liouville system, we have got f double prime is minus of lambda f, and we have said that p, once again, which was that p y prime, the whole prime term that was there, that is that p that is sitting in here. There was a qy and there was a w lambda on the right side. So this is this p which is sitting in there. The periodic Sturm-Liouville system is one which has got p minus l equal to p of l, and in this particular case it is unity, so it does not matter. But f of l is equal to f of minus l, and f prime of l is equal to f prime at minus L. Okay, so this is the periodic system. And we'll do this lambda equal to 0 business for one last time. So you have got lambda, lambda can be 0, lambda can be positive, lambda can be negative, and if lambda equal to 0, you get f double prime is ax plus b. Okay, f double prime is 0, so f is equal to ax plus b. Okay. All right, so if fl is equal to minus fl, so if fl is al plus b is equal to f of minus l, which is a minus l plus b. If you do this, then it's very clear that a is going to be equal to 0. Okay. So there's nothing very significant about this. Now, if a is equal to 0, right, then f is equal to b. F is equal to b. Is f equal to b a valid solution to this situation? Essentially what we are saying is lambda equal to 0 something which is an acceptable eigenvalue? Is b, f equal to b a solution to this? Well, look at the original equation. Okay, the boundary condition, the original equation gave me ax plus b, and you had f prime of L is equal to f prime of minus L. So we have used up one condition. The second condition is that getting satisfied? B is a constant. If B is a constant, then f prime this is equal to f prime this is equal to 0, which means for the first time we are seeing lambda equal to 0 does not end up with a trivial solution. Okay. So lambda equal to 0 is a valid eigenvalue. Okay. And the eigenfunction is f equal to b, which is a constant. Okay. So this is a valid eigenvalue. Okay. So lambda equal to 0 so far in all of the situations we had seen was giving us trivial solution. Now it no longer says we'll have to handle that. That's about all that it means. Okay. So consider the next option. The algebra now I will not do because this is something which is same as the earlier algebra that we had, which is to say that you are going to get the exponential solution, and then again you put in the boundary conditions, do blah 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 algebra, and you are going to get a trivial solution. Okay. So the algebra is all given up here. I'm not going to repeat it here. Okay, but you can go through it. Okay. I don't know. There may be a case on the exam where this fellow also is going to end up with a non-trivial solution. Okay, I have no idea. Okay, but all I'm saying is that you need to do the algebra. We have done the algebra n number of times now, so we are not going to do that. We are only going to do the algebra which is of interest to us, which is lambda equal to minus k square. So lambda equal to minus k square. So I've got lambda equal to minus k square. So this guy is minus k square of f. So what is f therefore? F is equal to what? If f double prime is minus k square f, what is f? Sines and cosines. Okay. So a cos kx plus b sine kx. Okay. So this we have done n number of times now. The reason why we are looking at this is because this comes up with some nice solutions. Okay. So f of L is equal to f of minus L. This is one of our conditions, right? We are talking about a periodic Sturm-Liouville system. That's a Sturm-Liouville system. We have already shown that it's a Sturm-Liouville system. And so Fl is equal to f of minus L. So Fl is equal to A cos KL plus B sin KL is equal to A cos minus KL plus B sin minus KL. So this is Fl equal to, this is f of minus L equal to that. What does this give me? What does this give me? This expression here. What is 0? It's not identically 0, right? So this guy is equal to this guy because cos minus k is equal to cos k. So these two terms are going to go away, and you have got sine of minus k is minus sine k. So I pull this guy to the other side, and what we get is b sine kl is equal to 0. What can I say now? What can I say about the solution now? Can b be 0? Or should b be non-zero? This is what is the condition that I am getting. So what happens if b is 0? In the past, whenever we have come up with such a situation, b equal to 0 meant a trivial solution. Now it is not necessarily, not yet at least. Okay, so b can be 0, and if b is 0, then this guy is non-zero, and if this guy is non-zero, then b is going to be equal to 0. I am just putting b is non-zero there, but as yet we cannot make such a statement. Okay, so we'll just leave it hanging for 1 minute here and say b sine kl is going to be equal to 0. Look at the next condition now. Okay, what is the next condition? The next condition is f prime of L. F prime of L is f prime of minus L. So if f prime of L, so f prime of L is A cos is sin kx plus b cos kx. There's a k hanging in there and that. Okay. So f prime of x is equal to this, and if I put, so this is f prime of x, and so f prime of L is equal to minus of ak sin kl plus bk cos kl is equal to minus ak sin minus kl plus bk cos kl. So again the cos is going to go away here now, and you get a sin kl is equal to 0. Now I have got these two guys here. Okay. So the earlier condition gave me a cos kl, a sin kl equal to 0. The other condition now gave me a sin kl equal to 0. Now what can I comment on a and b? Now I can say that if I want a non-trivial solution, a and b have to be non-zero. Okay. So I just jumped the gun a little bit when I said that b is non-zero there, but it's not wrong. So you have this guy and this guy have to be non-zero to get a non-trivial solution. So sin kl is equal to to 0. Which means what? KL equal to n pi. Which means that now my solution is f is equal to a cos n pi x by L plus b sine n pi x by L. What is this? Have we seen this in the past? The solution to the Sturm-Liouville system, which was this guy here, okay, a periodic Sturm-Liouville system with those as the conditions, ended up with the solution as being this, where these are the eigenfunctions and n is an integer. Have we seen this in the past? This is nothing but the Fourier series, right? It's not exactly the Fourier series. I'm saying it is the path, so-called, to build my Fourier series. Okay. Why? Because this f, which is the solution of this, and what did we say about the Sturm-Liouville system? We said that each of the eigenfunctions were all orthogonal. If my functions or eigenfunctions are all orthogonal, then we can clearly now say that y, where y is any function now, doesn't matter what it is summation of a sine n pi x by L plus b cos n pi x by L. What is missing here? Was this the Fourier series? There was one constant hanging in there. And can we put the constant here now? I can't do anything I want, right? But can I do it now? Yes, because lambda equal to 0 was not giving me a trivial solution. Lambda equal to 0 ended up with an eigenfunction being a constant, right? So lambda equal to 0, this guy is the contribution of that lambda equal to 0. These are the other contributions of the lambdas, okay? So in some sense, this is going to give me the Fourier series. It doesn't give me the exact Fourier series because they are not orthonormal, right? But what you can see is any function now y, which is in that periodic or which conforms to that periodic Sturm-Liouville system, is going to be representable like this, which is your Fourier series. Okay, I think we'll stop here now.